Hello, welcome back to our gas laws lectures. We are going to look at the specific laws this time that govern our gases. First one we have is Boyle's law, and it states that when temperature is constant, pressure and volume have an inverse relationship. So when it says temperature is constant, that means that in the initial conditions and the final, the temperature is the same. So we essentially ignore the temperature. Um, when I have a high pressure, I'm going to have a smaller volume as compared to when I have a low pressure inside, I'll have a higher volume. A way to look at that is if I have a whoopee cushion and I sat on it and I am putting a high amount of pressure on the outside, which is making the volume smaller on the inside. Here we have our pressure, and this can be in any of the units that we talked about previously. We can have torr, millimeters of mercury, we can have ATMs. The only thing we have to keep in mind is that this one needs to have the same units as this one. Same goes for any of these equations. The units for the initial and final have to be the same. And then here's my volume. So I can have liters, milliliters. Those are generally the ones we're going to have. But just remember that if you have milliliters over here, your answer is going to be in milliliters if you're looking for volume. So you need to make sure that your units are what you want. So let's take a look at Boyle's law kind of in action. So here I have an example. It says the volume of air in the marshmallow blaster is 450 milliliters. The pressure is 118. If I decrease the volume to 50 milliliters, what will the new pressure be? So first I'm going to highlight what we have. We have volume and pressure, and then we have a final volume, and it's asking for pressure. So this is how we know that we're looking for Boyle's law. So if we take this and we set it up, we're going to take our equation, which is P1V1 equals P2V2, and now we're going to plug in our values. So I have 1 ATM for my initial temperature times my volume, which was given as 450 milliliters. Make sure you put units so you know everything that's going on here. And we're looking for pressure, so I'm just going to leave that as P, and it's going to be times our final volume, which they told us was 50 milliliters. Now our volumes are in the same units, so we're good, and we're going to get our answer in ATMs. Now, when we solve this, I get 450 equals 50 times P, divide by my 50, and that's going to give me P equals 9 ATMs. And I know it's in ATMs because that's the pressure that we start with. So that would be our answer. Now when you do this, make sure that if you're given an initial volume in liters and then a final volume in milliliters, that you convert one of them so that everything's in the same. Otherwise it's not going to work. So let's take a look at our next law. Oh, and before I forget, when you plot volume over pressure for this, if pressure is increasing this way and volume's increasing here, it's going to make a graph that looks like this. So this is an inverse graph. As my pressure increases, my volume's going to decrease. So over here I have a high pressure and a low volume. Over here I have a low pressure and a high volume. Alright, so Charles' law says that when pressure is constant, so we're looking at constant pressure, so it's not going to be in the equation because it doesn't change. Temperature and volume have a direct relationship. So here we're looking at our volume, our initial temperature, our final volume, and our final temperature. So if I look at this, I have an initial volume and an initial temperature. If I add heat and I raise the temperature, then my volume in a container that can expand is going to increase. So this happens because the added energy in the form of heat makes the molecules move faster, and they're bouncing around this container harder, which is causing more pressure. It's causing it to expand. So Charles' law is going to have a graph that looks like this, just a straight line when we graph our volume and our temperature. Let's take a look at a Charles' law problem. So if a balloon is inflated to 300 milliliters, so we have volume, and 20 degrees Celsius, is placed in warm water bath and heated to 70 degrees Celsius, what is the new volume of the balloon? So first we're going to write our equation. Since we have volume and temperature and that's it, we know we're going to have our V1 over T1 equals our V2 over T2. Now, something we need to remember when we're using temperature. We cannot use Celsius. We can't use Fahrenheit. We can't use Rankine. We have to use Kelvin. When we solve gas laws, you must use Kelvin. You must use Kelvin. So we have to convert our temperatures, because we were given Celsius, to Kelvin. So our conversion is 273 plus our degrees Celsius, which is 20, is going to give us 293 Kelvin. So that's going to be our initial volume, or sorry, our initial temperature. So we have 300 milliliters over 293 Kelvin equals, we're looking for our new volume, which is going to give us an answer in milliliters. And then we need to get our Kelvin degrees, because we can't use our Celsius. And that is going to give us 343 Kelvin. So I'll put that down here. Now if I cross multiply across here, so I'm going to multiply these and these, I will get, let's see, a final volume. Actually, it's going to be 102,900 equals 293K. And then when I divide by 293, it's going to give me our volume of 351 milliliters. So that is how we solve our Charles' law. We just have to make sure that it's always in Kelvin. Always, always, always in Kelvin. Let's take a look at our next gas law. Here we have Gay-Lussac's law, and it states that when volume is constant, we have pressure and temperature having a direct relationship. So this is going to give us a graph that looks like our last one for Charles' law. So just a straight line when we look at our pressure and our temperature. And in action, let's take a look at a problem. So first we're going to write our equation, which is going to be P1T1, sorry about the writing, equals, does not like those equal sign, P2 over T2. Sorry, it's a 1. Alright, so the pressure inside a truck tire is 1.25 ATM. So here's our pressure initial, and our temperature is 50 degrees Celsius. What is the pressure in the tire when the temperature is 10 degrees Celsius? Now, once again, we need to convert both our temperatures to Kelvin. So we have 273 plus our 50, and that's going to give us 323 Kelvin. And then we have our 10 degrees plus our 273, and that's going to give us 283 Kelvin. Alright, so now we can start putting in our values. We have 1.25 ATM as our initial, or our P1, over our 323 Kelvin, and that is going to be equal to our pressure 2 over our 283, and put Kelvin there. Now if I cross multiply again and solve for P, then I'm going to get an answer of 1.095 ATM. So if we look, it got colder, so the pressure went down. So that makes sense. They're moving slower, the molecules, and therefore they're not hitting the outside as hard, so they're creating less pressure. Now, real quick, let's take a look at our last law. This is called the combined gas law, and it just combines kind of all the laws into one. So if you see here, we have, this is our Gay-Lussac's law. Here we have our Charles law, and here we have our Boyle's law. So all you have to do really is just remember this one law, and you got all of them. Whichever one is being held constant, so let's say I'm not changing my temperature, then I can just kind of cover that up and pretend it doesn't exist and just solve for P1 V1 and P2 V2. Or if I have a constant volume, it's not going to change, so I can just leave that out of the equation. Now for our example, we have air in a dry sealed 2-liter soda bottle, has a pressure of 0.998 ATM and a temperature of 34 degrees Celsius. What will its pressure be if it's brought to a higher altitude where the temperature is only 23 degrees Celsius? Now, if we write our equation, we have P1 V1 over T1 equals our P2 V2 over T2. We have to convert our degrees Celsius, so we have 34 degrees Celsius plus 273, and that is going to give us our 307 Kelvin, and then our final one is 23 plus 273, and that's going to give us 296 Kelvin, and now we can fill in all our values. So my initial pressure is going to be 0.998 ATM. Once again, I apologize for the less than spectacular writing. Times the volume. Here we have 2 liters. And then our temperature for starting was our 307 Kelvin. We're going to have, looking for our pressure, our volume actually didn't change because the container didn't change. So that's where our final volume came from, is actually just the same. And then our 296. And that gives us, when we cross multiply again, we are going to get an answer of 0.962 ATM. So that is how we solve our combined gas laws. So for right now, that's all we're going to look at, and we'll see you next time. Have a good night.